Bing. Okay. So here we are today. So the first handout, that kind of just 2 pages, because I wanted to give you a choice. Wow. Is this the exercises from class? Because I ran out of exercises. We've got one to finish up from last day. But then if you want to keep working at it and get really good at it, I thought, well, how about we do those odd exercises that I'll be posting the solutions to anyways, but as a handout, or there's also the logic handout, which is next on our bucket list. And so we can spend as little or as much time on the minimization problems as you want, or we can start, well, we'll finish the one from last day. We're gonna do logic. It's just a matter of when. So next week. So it just depends on what you want to do. At least I'm all prepared. I was saying to well, they're my friends, but in my office, like I've never simultaneously been so prepared, but also so disorganized at the same time. So I feel like I had to go print, do all the stuff. So I was trying to figure out what to do that we could squeeze in as a complete topic before the test, which is on February 11th, which is the Tuesday before reading break. Which I had it on the Thursday, and then I thought, that's kind of rough, right? So close to reading break, no one's gonna want to be here. And so I moved it to the Tuesday, the 11th. Okay? And so what I want to do is maybe start logic today. We'll see how quickly we can work through those problems. I gave you the lines this time. That's nice of me. All right. And then we'll do review, and then we'll have the test. And then I don't know. What do you do the Thursday before reading break, and then you have a week off, and then what? You just review it again? I don't know. We'll see. What do we do? But, oh, and then I posted this, which I think is pretty cute. But you have to click on it. It used to play just on the page. This is the important stuff for me. Anyways, my plans for reading break, it should say. So you've got the handouts. Now I want to know. Well, you can think about it for a little bit longer because we have a problem to finish up. What? We do? We really do. We were kind of working on this. Well, we were actually. I'm going to copy this. Somewhere. I guess you'd have it on a printout somewhere. I was so cold when I got dressed this morning, but all day I've been like, whoo. So, okay. Professor Hamer is on a low cholesterol diet. I didn't bring any of those spare. You weren't here last day, sorry. You get to read it on here. During lunch at the college cafeteria, he always chooses between 2 meals, pasta or tofu. The table below lists the amount of protein, carbohydrates, and vitamins each meal provides, along with the amount of cholesterol he is trying to minimize. Okay. Mr. Hamer needs at least 200 grams of protein. Don't worry, it's per month, which is hilarious. 960 grams of carbohydrates and 40 grams of vitamins for lunch each month. Over this time period, how many days should he have the pasta meal and how many days the tofu meal so that he gets the adequate amount of protein, carbohydrates, and vitamins, and at the same time minimizes his cholesterol intake? Okay, do you remember where to start? Figure out what your objective function is. Yeah, I knew what you meant. We want to minimize the cholesterol. We do that first because it helps guide us towards which one I can call my X and which one I can call my Y, right? And so here we want to minimize the cholesterol. And I did notice that the units are different, right? These are all in grams, and then these are in milligrams. But in this case, because we don't map the cholesterol on the same graph, it's okay. But you could rewrite these in grams by dividing by, is it 100? Or just leave it. But because the cholesterol is in the objective function and kind of separate, right, it's okay. Otherwise, you would need to make an adjustment. Like you have the Silly Nut Company or whatever it's called. Yeah. If I write it like this, I get 60 milligrams from the pasta and 50 milligrams from the tofu from each meal. And then that helps me identify that, okay, let's let this be my X, my pasta be my X, and my tofu be my Y. So my next step is to say what my X and my Y are. Of course, you could let X be tofu and Y be pasta, but to me, that's really confusing because that's not how they appear in the table. Okay? And so let X be the number of pasta meals, and Y is going to be the number of tofu meals. It helps to, so just saying X is pasta and Y is tofu, that's fine, but it helps to highlight that it's the number of those meals, right? Because then we can kind of think about it that way. Okay. We had some constraints on the diet, right? And so if you're a dietitian, you would probably be familiar with something like this, although I'm sure they give them nice software to work with, but it's just doing this. Right. So what are our constraints? Our constraints, we have constraints on how much protein he needs to eat, how much carbohydrates he needs, and how much vitamin C he needs. So on the protein, he gets 8 grams from the pasta and 16 from the tofu. So depending on how many of each, 8x plus 16y is the combined number of proteins or grams of protein that he gets from X and Y meals. Now we have restrictions on these. Needs at least 200 grams of protein. I just think it's so funny. Greater than or equal to 20. For the carbohydrates, we do the same thing. 60 times X plus 40 times Y we have to have at least 960. And then finally, vitamin C, 2 and 2. And they have to be greater than or equal to 40. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. Those I would consider kind of optional constraints, right? Because you're not going to have a negative number of meals. And so X greater than or equal to 0 and Y is greater than or equal to 0. Right? That just restricts you on your graph, right? Lets you focus. Okay, so now you spent some time figuring out how to draw lines, right? Because I have more exercises where I drew the lines, well, kind of sloppy, but took a screenshot and drew on it, right? Which is what you still want to do on the test. Okay, so then how about, well, it won't really make sense to do it incognito, but how about I just plug these guys in. 8x plus 16y, I'm going to say is equal to 200 because that's going to give us the line. And then we can do some practice figuring out which side of the line we need to be on. And then we have 60x plus 40y equals 960. And 2x plus 2y equals 40. I'm going to take a screenshot and it might be loud or not. I didn't tell you which line was which, right, on the next handout. And so, right, so then you'd have to figure out your constraints and then figure out which constraint is line 1, line 2, and line 3. Right? But here we have them color-coded, and let's just go for it. We want all of these to be greater than or equal to, right? Which I suspect when I'm looking at these, right, I'm going to be on this side of all these lines, right? But you can pick a point just to confirm, right, that it's true, that it's giving you a true statement. And so let's pick a nice number. How about, oh, a nice number might be 2020. With 2020 as my test point, right? Then what I can do is I can plug in x equals 20, y equals 20, and as long as it's greater than 200, right, the result, then that is the area that I want, right? And all the points in that same area on that side of the line will satisfy it. Yeah. And so if I do 8 times 20, oh boy, I better not have forgot my calculator today. Let's do the green one. 8 times 20 plus 16 times 20. I get 480, which is greater than or equal to 200. Just as I suspected, right? We're really just kind of confirming what we suspected. So then For this green line, I need to be above this on that side. Then we've got the purple line, which is at 60. And if I plug in 20, x is 20 and y is 20, 40 times 20, I get, and let me just give myself some more room here. Bing. 60 times 20 plus 40 times 20 is 2000. That's great because that is greater than or equal to 960. So for the purple line, it's hard to see on the screen there, but for the purple line, again, we're just above. You don't have to do this. If you're comfortable with just picking the side of the line that you want, then I'm okay with that. It's just nice to be able to check it, right? And talk yourself into it. I'll use dark blue for this. Do I have black? I guess. Weird. I don't think I've ever written in black on here. 2 times 20 plus 2 times 20 is 80, which is greater than or equal to 40. That's great. Got that great debate of, okay, do you shade the area you want or shade the area you don't want, right? With practice, you'll be able to see that, okay, well, all of these have to be satisfied at the same time. So for me, I see myself kind of going like this, and kind of more importantly, just to there and to there. And the only reason I'm doing that is to figure out the vertices. Our next stop. The vertices that I want. The vertices that I want is this one, this one, this one, and this one, because I forgot something. X greater than 0, y greater than 0, which means I need to erase some of this highlight. Right, x greater than 0, y greater than 0. Oh boy. Which also means I need to erase this highlight. Can I do that? Hey, that's pretty good. Okay. So I have 4 vertices. As long as you label them reasonably, right? For the maximization problems, if we have the origin, I like to start at the origin and loop my way around. But here, I guess I kind of go against my own rules. And I start here at the top and I go A, B, C, D. But you have to label them. And as long as you've labeled them, do me a favor and do them in some sort of order, right? Otherwise, I have to really look at it. And no one wants that. Okay. What's our next thing? We have to find those vertices. Okie dokie, artichoke. Vertex A is the intersection of, it's not very obvious here, but the purple line and x equals 0. And the purple line is so this is the intersection of the purple line, which is 60x plus 40y equals 960, and x equals 0. you can rearrange that into y equals mx plus b. In this case, I find that it's a little bit easier probably to just plug in x equals 0 right away. And so that's what's nice about the intercepts. So I get 60 times 0 plus 40 times y is 960, which leaves me with 960 divided by 40. So y must be 24. So that vertex is when x is 0 and y is 24. Which I really hope is what I had in that screenshot from last day. Hope. Nice. How about B? B is the intersection of, oh, that's hard to see, the black line and the purple line of 2x plus 2y equals 40, and the purple line again. Yeah. 60x plus 40y equals 960. You could use the elimination method if you want, right? I prefer substitution for myself, but it's up to you. How I'm gonna do it is I'm gonna solve both of these for y. Just kind of force them all to be y equals something. And then I'm gonna set them equal to each other. So I get 2x plus 2y is equal to 40, makes 2y is 40 minus 2x. So y is 20 minus x. Doing some quick cancellation there. Same thing on this side, 60x plus 40y is 960. So 40y is 960 minus 60x. Well, that doesn't divide nicely, does it? 960 divided by 40 is okay. 60 divided by 40. I'm gonna go for 1.5 times x. That's nicer. Instead of 60 over 40 or 3 over 2. So now I can set these two equal to each other. Right? If y is equal to this first one and if y is equal to the second one, then I can set them equal to each other. So 20 minus x should be the same as 24 minus 1.5x. Choose your own adventure. However you want to move things around here. I'm going to move my x's to the left-hand side and my non-x's to the right-hand side. So I get negative x plus 1.5x is 24 minus 20, which leaves me with 0.5x is equal to 4. Okay. At x equals 8, you can use either of the equations to figure out what y is going to be, but let's use 20 minus 8, which means that y is going to be 12, which means the intersection is at 8, 12. Let's just check against the graph to make sure that that makes sense. Well, first, I should probably check this guy makes sense, 0.20, 0.24. That one makes sense. Is this one looking like 8.12? It is. That's a relief. So now we can move on to C. C is the intersection of the black line and the green line. Man, a lot of intersections on this thing. Usually they're like the intercepts and you already solved for them or you know what they are. It's the intersection of the green line, 8x plus 16y, 200. And the black line, 2x plus 2y. Same deal. Right? You can use elimination if you wanted to. Right? This one kind of lends itself to elimination. You could multiply this one by 4 to eliminate the 8x. Let's try it by elimination. It would look like this. I have 8x plus 16y is equal to 200. And then I have 2x plus 2y is equal to 40. This is just for getting flexy. But what can you do? You can multiply. If the goal is to eliminate one of these variables, what if you multiply the second one by 4 and subtract it from the first one? Then I get 4 times 2, which makes 8. And 8x minus 8x makes 0x. 16 minus 8x, or sorry, 16y minus 8y makes plus 8y. And then 200 minus 160, confirmed, is 40. Just thought it was weird that we got back to 40, but checks out. Which means now I can solve for y and say that y is 40 divided by 8, which is 5. And now I can plug in y equals 5 and solve for the x. Kind of reverse of what we're used to doing. So 8 times 8x plus 16 times 5 is equal to 200. 16 times 5 is 80. 200 minus 80 is 120 divided by 8. X is 15. Which means the point of intersection is at 15, 5. Clean that up. Does that look reasonable? It does. That's great. D. D is a nice one, right? It's the intersection of the green line and y equals 0, right? So try to keep it on this one page here. The intersection of the green one, was it 8x plus 16y is equal to 200? Is that the green line? Are you guys impressed or what? That's always my goal with teaching. Can I impress them with my memory skills? And y equals 0. Well, there's only 3 to choose from, so don't be too impressed. 8x plus 16 times 0 is 200, which means that x is going to be 200 divided by 8, which is 25, which at y is 0, so then we are at 25, 0. Check it to make sure it makes sense. X is 25, looks good. Oh, it keeps, got sticky fingers or something. Oh, that's a lot of work, right? But it is a good way of testing. Do you know how to find the intersections of lines, right? And so that's why I like this problem so much. if we have A, B, C, D, we need the vertices going from bottom up here, 25, 0, 15, 5, 8, 12, 0, 24. Final step. Now we bring in that objective function, which is the cholesterol in this case, right? And we evaluate the cholesterol content at each of these vertices, and then we pick the minimum, and then we'll know. So the cholesterol, oops, there's an H in there, isn't there? Cholesterol. I don't know. I'm about to find out. Cholesterol. 60x plus 50y. It doesn't matter if you brought that up to grams to keep them all on the same scale, right? That's fine. Because the minimum wouldn't be affected. Okay, it would still be the minimum, it would just be a smaller number. You know? But like I said, doesn't matter because the objective function is separate. Okay? But if you want to be consistent, it's always good to match the units. But I haven't. 60 times 0 plus 50 times 24. 50 times 24 is 1,200. 60 times 8 plus 50 times 12. And this would be milligrams of cholesterol per month. Let's see here. 8 and 12. Don't hit the wrong key. 60 times 8 plus 50 times 12. I get 1080. What you guys got? Thank you. 60 times 15 plus 50 times 5. 1150. Times 0, 60 times 2. I want the minimum. I'm going to go with 1080. Should we have constraints on the total number of days? Oh, well, I've already finished the problem. I'm just thinking because now he only gets to have lunch 20 days, which is kind of reasonable. And that's the problem when you overlook a constraint, I guess. Yeah, so I mean, it kind of works out, right?
That makes sense. That's what we're calculating.
Yeah. Yeah, it wasn't until now that I realized my blunder. But how many days would he eat there?
At the college, only 5.
Yeah, 5 days a week. Done. Yeah, what's his problem? Here he's just eating like crazy. And here. Just so many. Yeah. Yeah. No, like, check in on the weekend, grab a meal. You gotta hit your targets, right? How would you incorporate if he eats on campus 20 days a month, how would you have done it? X plus Y has to be probably greater than or equal to 20, right? Could have baked that in there, but no. And I don't think we were meant to. Unless it says, and I completely overlooked it. But I'm not scrolling back up there because I don't want to know. I'm happy with this. So to minimize, whoops. To minimize the cholesterol to 1080 milligrams per month, he should eat 8 pasta meals and 12 tofu meals. Pasta meals and 12 tofu meals per month. Ignoring some constraints. You could force X plus Y has to be 20. Right? Crazy. Which would change your feasible set to be what? X plus Y has to be 20. Is that on here? Where did it go? Y is 20. Oh, it's up here.
It's on the black line.
Is it on the black line?
It's on the black line.
Oh my gosh. It is.
It's the same thing.
Okay, well, that's a relief. Oh yeah, 2x plus 2y. Hey, how about he eats there not 20 days, but 23 days a week? It would alter our feasible set. All right. Your new intercepts or vertices would be these 2 new ones. Anyways. Rendering all the other lines useless, making me think, nah, we didn't need to do that. Okay, so have you had a glance at the logic notes? Pretty fun. Like I said, we're gonna do it. But I also have these up my sleeves.
Oh, that was.
You got them both. You can try them. The logic? Well, buckle up. You're about to find out. Yes, just the right question. But at least you have these, and then you'll see what it looks like with the lines, and you have to figure out which line is which, right? And kind of work. Yeah, you still have to find your constraints and then match them to the lines and find the intersections and stuff. And so this is what I would expect you to be able to do on the test, right? And I'll post those solutions after class, so you'll have them. You can do them, try them. But let's do some logic. Okay, well, please stay on the line. I need to bring it in. I'll start a fresh note. So I'll post 2 files from today. Keep them split up. Okay. And just checking, everyone has the logic handout. Yeah. All right. Okay. So logic is not in the textbook. And so I've just put together a document for us. So this replaces the textbook. There are some exercises, and those are the ones you'll hand in for kind of your assignment work. Okay. And so I'll highlight those. But I will say it's not in the textbook. So this is what you get. But it also means this is all we're covering in terms of logic. There's a lot more that we could do, of course, like anything, but we're just going to start kind of hovering around in logic. And a lot of math people don't like it because it's very hard, but then a lot of non-math people really enjoy it because it's just kind of arguments and kind of lawyer stuff.
I love it.
Yeah, I think this might be the crowd for it. Usually everyone's like, oh, Jake, no.
We became friends.
So maybe you know already what a proposition is. So a proposition, did you do truth tables in there? Okay. We're gonna solve all these things with truth tables. Okay. So a proposition is any sentence where it can only be true or false. It can't be anything else. Okay. For example, 4 is even is either true or false. And then I ran out of, today it is raining. It's either true or false. We have math class today, till today. Maybe I should change it. You are enrolled in a math class. It's all true. Today it is raining, that's false, but it could be true on a different day. And so often what we do is we have these kind of simple propositions, but usually we combine these simple statements with words like and, or, oh, my highlighter's too big. Let me do this. And, or, not, right? 4 is not even is still a true or false statement, right? Today it is not raining, that kind of thing. Even things like today it is raining, or we have math class today. Thinking about whether that compound statement is true or false, right? We're going to have truth tables to help us determine that. We can even go as far as kind of if then and if and only if. And that's pretty much as far as we'll go with this stuff. So if we have 2 propositions, and each proposition has 2 possible truth values, right? It can either be true or false. There are 4 ways that truth can be assigned to 2 propositions. And I should say, I've got it later. I should have introduced it though. Oopsies. 2 propositions. Usually we use a generic P. P is the first proposition and a generic Q, which is the second proposition. So depending on if P is false or if P is true, so that brings me to my next thing. We use 0 to denote a false statement and 1 to denote a true statement. You can use F and T's, but they tend to look very similar if you're kind of writing a lot of them at the same time. And so I encourage you to use zeros and ones instead. Yeah. You could say or F or T. I'm going to use zeros and ones just because it's a little bit cleaner, right? And you can see how F and T's would kind of float together and start looking a lot alike. And so you don't want to avoid that. But here are the 4 possible combinations that we can have. Another thing I want you to notice is that, okay, if I have two propositions, I'm trying to remember if we go to 3. We'll cross that bridge when we get to it. You're going to start with 2 zeros and then 2 ones. And then for the next one, you're going to alternate 0, 1, 0, 1. And now you have all the possible outcomes, right? And so here you have all the possible combinations. This gives all possible combinations of PQ. So, jumping right into it. If P and Q are propositions, their conjunction, you don't have to call it the conjunction, but you do need to know what it is. It's and. So the conjunction is and. And is denoted by this kind of capital A without the bar inside, right? That's how I remember that that's and. Just kind of shorthand notation. Right, kind of morphs into this logical and. It's worthwhile seeing this now, because once we get into sets and probability, then we start just putting a curve on it for some reason, but it still means and, right? So having seen it now, it's going to pay off. And so even though it's likely new right now, right, it's worth getting to know it. And so and, right, has, well, this property here. So if P is false and Q is false, then both of them together, right, P and Q is also false. Overall, that makes a false statement. P is false, Q is true, P and Q must be false, right? It's kind of overridden by, if there is a false statement there, it's going to be false, right? As soon as you see a false, it's over, it's false, right? Here, P is true, Q is false. Again, now I have a troublemaker in Q, and so the overall statement is false. Right? The only time that it's true is if both statements are true, right? And so here, P is true, Q is true, so P and Q is true. Which one of these should we use? 4 is even. Today is raining. 4 is even, that's true. Today is raining. Should use 1, 0. So if I said 4 is even and today it's raining, that's false because it's not raining right now. I don't think. Well, I guess we'd have bigger trouble than rain, wouldn't we? I don't see anything. Huh? So that's and. the truth values for and are pretty straightforward, right? They both have to be true in order for the and statement to be true. And so to read this table, sorry, I stole this from another textbook, and it's very condescending. It's like, it should be obvious. And I tried to remove all that, but you must realize from another course where we do logic, and it's so condescending. But anyways, it even says stuff like, if that doesn't make sense to you, go back and read it again, which is pretty rough. It's true, I agree. If it, yeah, but I mean, you can say it nicer. So any one line represents a case, right? So a possible combination of P and Q. Okay. And then the numbers 0 and 1 are used to denote false and true, respectively. And then the order in which we list the cases in a truth table is standardized, just like we start at 0, 0, 1, 1, 0, 1, 0, 1, right? And so that's a good place to start. How about, I'll write out here, and. That's just the logical conjunction. Technical name, but if you call it and, it's okay. How about the logical disjunction, which is or? If I say 4 is even or it's raining today, that's true. Only one of those has to be true for the overall statement to be true, right? And so that's reflected in the truth table, right? And so the or is kind of the V, right? So you flip the A upside down and it's the other one. Like most things, I only memorized, kind of when I was learning this stuff, I only memorized the and then I just remember that the other one is or, right? And so you only need to remember one and then you have the other one, right? We'll have different symbols for the rest of them. So these are the only two that we need to keep track of. So or is a V. So logical or. And just as we said, as long as one of these is true or both, right, then the overall statement of P or Q is going to be true, right? And so here I would summarize this as for or, only one of P, Q. Notice how I'm avoiding the and the ors because they're going to start to mean special things, right? And so P comma Q need to be true. Ugh. I guess I should finish the sentence. For the overall statement to be true. If P is a proposition, so logical negation, I kind of call it not, right? Logical negation, we have a pretty good handle on probably. So if P is a proposition, its negation, not P, is denoted by this little kind of hook. Okay? Sometimes we use the tilde, right? Depending on what resource you're using, it's good to be familiar with the tilde, but I like the hook. And you're going to read that as not P. So this you're gonna read as not P, or depending on what it is P is, maybe you're able to negate it, right? For example, if you have to negate 4 is even, you would say 4 is not even, right? Today it is raining, today it's not raining. We do not have math class today, right? Negating those statements. Okay. We can negate a combination, okay, which we'll look at. But for now, right, if you negate P, if it's 0, then if you negate it, it becomes a 1. And if it's true, then it becomes false, right? Flips back and forth. Okay. Look at us go. Page 1. Nice. I know. Just banking some intel. Acres of time. Nice. For the problems we're gonna do. So if we consider these propositions, and then I've got something for us to do later on, but I'm going to quit if I don't get a raise. So just kind of notice the sentence structure. If I pass the final, then I'll graduate. I'll be going to the movies, provided that my car starts. These are all what we call conditional statements. I didn't want to keep you in suspense any longer. So these are all conditional statements. So these are all conditional statements. And that's because they can all be restated into the form if blank, then blank. Okay. And so what we're going to do is we're going to rewrite each of those statements in the if this, then this form. Okay. And so I want you to try it, and then we'll do it together. And I don't think it's going to take very long. So I'm not going to pause the recording. Ugh. Mm-hmm. Into the form, if this, then this. Then I'm going to quit. I know, I think you guys are taking it way harder than I meant. Not yet. I'm building up to a new thing before we use a table. I guess it's I will be going. Okay. I guess I didn't pause the recording. Well, here we go. I know, you guys took it way too hard. Like, can I assign a P and a Q to this and make a table? Yeah, we will, but calm down. I just want it in the if this, then this format. So if I don't get a raise, then I'm going to quit. This one was already in that format. If I pass the final, then I'll graduate. If my car starts, then I will be going to the movies. So sometimes it's a little bit buried, right? And the reason you want to highlight and rearrange all these if-then statements into this format is because then you'll be able to manipulate it in an easier way. So a conditional statement is supposed to be a guarantee. So the truth table, I think, for a conditional statement is not intuitive, but it's supposed to be a guarantee. And so if you have a conditional statement, if P then Q, which we're going to denote by this little arrow, right? P comes first, and then you have the arrow going to Q. If P, then Q is how you're going to read that. Then we get this truth table. If P is P is false, Q is false. If I go from a false statement to a false statement, that conditional statement is true. That's weird to me, at least, right? Kind of, oh, okay, that's weird. But I've got an example where it kind of clarifies why that is. Okay? In fact, the only time that the conditional is false is if I start with a true statement and then the conditional is false. Yeah? And so this is the only time the only false combination of PQ. Right? So as an example, what if your instructor, some other instructor, not me, said, if you receive a grade of 95 or better on the final exam, then you will receive an A in this course. Okay? So then your instructor, shall not be named, has made a promise to you. Okay? If you fulfill that condition, then you expect the conclusion of getting an A, right? But there are other possible scenarios, right? And so first thing we need to do is, if we take the, can I just grab this? I know, cheeky. Copy, paste. Hey. That almost looks like it was in there. It gets bigger, but that's okay. So the first thing you want to do is let's assign a P and a Q, right? A generic P and a Q to these statements, and then rewrite it with the logical notation with that arrow that we've seen, because we know that this is an if-then statement, right? And so if first part, let's call this P. So P is now you receive a grade of 95 or better in the final exam. That can either be true or it can be false, right? So it's a proposition. Nice. Then you will receive an A in this course. Let's let that be Q. That can either be true or false, right? And so if we map out all these different scenarios with our first truth table by hand here, we're going to have P and we're going to have Q. And we only need 4 rows, but there's a lot of kind of explaining going on for each row, so make them kind of lofty, right? And remember, you're going to start with 0, 0, 1, 1. Hopefully I don't need more room. Then starting at 0, 0, 1, 0, 1. Just make some lines there. They're all sloping. Oh well. Let's add if P, then Q. We'll just blindly take it from the table above, right? And then we're going to confirm and kind of talk ourselves into it, hopefully. Or you can just remember that the only one that's false is 1 to 0. But 1, 1, 0, 1. Okay. Thinking about what P is, what color can I use here? Let's do dark blue. And the explanation, right? These are all the possible scenarios. Nothing else can happen here. If P is 0, that means you didn't get a grade of 95 or better. Womp womp. So you didn't get 95 or better. And you also didn't get an A in the course. Though upsetting, you wouldn't really pursue anything. You didn't fulfill the initial statement, right? If you get 95 or better, I'll give you an A, right? You didn't get 95 or better and you didn't get an A, but you're not going to be, terribly upset about that because it's all true. It all checks out. Right? And so that first statement, okay, fair enough. That is true. Right? The next line, if you didn't get a 95 or better, you could still get an A in the course, right? Just by your own merit, right? And so here, right, you did it on your own, didn't get 95 or better, but got an A in the course, right? You worked really hard and you didn't need to get 95 in order to get an A in the course, that can still happen. And you're not going to go back to your instructor and say, hey, you said, right? Because you didn't get 95 or better. So far we're kind of, okay, relaxed about it. It's this next one where we would be up in arms. What if you did get 95 or better? But then he's a liar. He didn't give you an A. That's bad. So here, you got 95% or better. Just said 95, I guess, or better, but didn't get an A. That's more of like, oh. Bad. He's a liar. And that's why it's false. Whee! And then we're back to happy again. Got over 95, and you got an A in the course. Got 95 or better. and got an A. Whee! So although it's a little counterintuitive when you first look at it, right, look at those truth values and how they line up. If you kind of break it down like this, then it does hopefully make a little bit more sense. Okay. The converse of a proposition if P then Q is defined as if Q then P. So what I want you to do is take this statement here, and I'll nab it like this. Copy. I'll paste it up top here. And what I want you to do is rewrite this statement, right, which is if P then Q, and rewrite it as the converse, which is if Q then P, which would look like what? We've got more of these to do. So let's do this one together. So now we're flipping it and we're saying, okay, if I get an A in the course, kind of flexy on the terminal or how we say stuff, or if I will receive an A in the course, then I will receive a grade of 95 or better on the final exam. Are those the same? They're not equivalent statements, right? If you kind of think about it, but I'm getting ahead of myself. So it would look like this. If, can I do a shorthand version? If I get an A in the course, then I got 95 or better on the final exam. There's a way to get an A in the course even without 95% on the exam. Right? We all kind of know that. And so that's not an equivalent statement, right? And so here, notice if P then Q is not equivalent to if Q then P. Don't worry, there is one that is logically equivalent, and it's called the contrapositive. The contrapositive of a statement, if P then Q, you're kind of probably starting to see the value in being able to rearrange a sentence into a if P then Q type of situation, right? Which is what we started with. Then the contrapositive is not Q. So if not Q, then not P. Uh-oh. Which means what? You have to negate Q and you have to negate P. Kind of think about those in your head. And then if the negation of Q, then the negation of P. Can you write that out in this sentence? It's kind of the previous sentence. You just negate each of them, right? There you go. Which is logically equivalent to the first statement. Score. This is really fun. I don't know if you're enjoying it, but it kind of feels like it. And I don't think I've ever had a group enjoy logic. So good job, guys. If I do not get an A, the course. Then I did not get 95 or better on the final exam. There's a third and final variation, which is the logical inverse. And the logical inverse of if P then Q is if not P then not Q, which is it's going to have the same logical meaning as the converse. So there's kind of different matchups. Let's write the logical inverse. I'm not going to make you memorize what the logical inverse is in the contrapositive and the converse. I'll tell you what they are, but you do need to be able to attach P's and Q's and rewrite the statement in an if P then Q, and then rearrange it from there.
Those counts for those on the formula sheet then?
Yeah, I'll put those on the formula sheet. Yeah, that's too much memory space. You don't need that. I need you to use it for your linear programming. So, what was the original statement? If I did not get did not get 95 or better on the final exam, then I will not get an A. In the course. Oof. Oh, I gave you so many examples. How about I pause it and I let you do it? If it snows today, then you have the day off. Wow, nice. And you have to write the converse, the contrapositive, and the logical inverse of that statement. And then do the same thing. I will do well in all my courses if I study. Ooh, curveball. For these, I'll pause it. Give you some time. Resume. Let's see here. Ta-da! And I might have mucked these up, so I do want you to check me. For the converse, I have, if we have the day off, then it snowed today. For the contrapositive, I have, if we don't have the day off, then it did not snow today. For the logical inverse, I have, if it does not snow today, then we do not have the day off. Nice. Main part was rearranging that statement into a if P then Q situation, right? And so the key is the if I study was at the end, right? But don't let that trip you up. You can rearrange the statement to be if I study, then I will do well. And then I lobbed off the rest because I'm lazy in all my courses. If I do well in all my courses, then I studied for the converse. If I don't do well, then I did not study. Which is the one that's logically equivalent to the first statement. Right? And then for the logical inverse, I have, if I don't study, then I will not do well. Nice. Good job. Next up, the biconditional. The biconditional is the conditional statement, but in both directions, right? Hence the term. And so if we have P and Q, then for this, we said if P, then Q, right? And so then if we can also go the other way, then we could read this as if Q, then P, right? And so together they make P if and only if Q. Oh, sold already. So this makes P if and only if Q. So it has to go both ways, right? And so what that looks like in terms of a truth table here is we can go back to the conditional statement, which said that, okay, the conditional statement, if we just talk about the conditional for now here, or maybe I should do this. If P, then Q. Oh, how about this for an exercise? Oh boy. I didn't give myself any room. Move this over here. If P, then Q, we already said was going to be the only time that that's false is if I start at a 1 and I go to a 0, right? And so then 1, 1, 0, 1. What if we read it the other way? We can figure out the truth values for if Q, then P, right? We just need to read it the opposite direction. So now I'm going from 0 to 0. That's true. From a 1 to a 0, right? I don't like that. That's the only time that I get upset in the conditional, right? And so that makes this a 0. From a 0 to a 1, I'm okay with that. Right? Think about it. You didn't get 95 on the final exam, you can still get an A, right? That's okay. And so here, and then if both of them are true, then that's true. So for the biconditional, they have to have the same value, right? It has to be this. Well, let's bake this in here. And right, has to go both ways, right? And we can write as this. I never actually spend any time developing it. I just kind of, here it is. But makes sense. And so now let's do another column. Let me move this over. I'll make it nice and clean. Sorry. By making a mess in your notes if you already wrote it down. What if we want to have if P, then Q as one thing? I already have a column there. And if Q, then P. That can make one new thing. Treating, this is now your first column, right? This is now your second column. So you've kind of created new columns that you want to be working with, right? And so the and, right? In order for and to be true, right, then they both have to be true, right? I say, oh, 4 is even and it's raining. No, that's false, right? Both statements have to be true. And so first one is true and the second one is true. I'm happy. First one is true and first one is false. No thanks. first one is false and the second one is true, I'm still left with, whoops, false. And then first one is true, second one is true. So together they are true. What's an easier way to summarize that instead of developing this table? You can kind of use it to get there. But when's the only time that you get a 1 here? Is if you're bouncing between the same values, right? Between 0 and 0 and 1 and 1, right? So notice the biconditional is true only when both P and Q are true. Or sorry, are the same, not necessarily true, because they can both be false, right? Notice the biconditional is true when P and, I'm going to use P comma Q, have the same truth values. Otherwise, it's false. Some more. We can finish this page. Nice. Good sports, all of you. This, I tried making it kind of nice and condensed just so that you have kind of equivalent forms of if P then Q. Yeah. Just so you can maybe recognize it on the test. I'm not going to try to set you up or anything. The biggest curveball that I might do is maybe, just maybe, giving you something like this where you have to first rewrite it in an if this then this statement, right? But nothing like P implies Q. Okay, fair enough. Q follows from P. Well, that seems lofty. P only if Q. Q if P. P is sufficient for Q. So this is the one that I used, right? If, I can't even remember what it was. If I study, then I got this. I got an A or I did well or something. P is sufficient for Q and Q is necessary for P. Well, but if you study philosophy, you'll definitely need all of these. So they do a ton of logic. My brother-in-law teaches philosophy at U of C, and so we talk about kind of teaching and courses, and the only courses that we have that overlap is all logic, which I hate. This stuff I love, but yeah, it's like, no, because it's the contrapositive and you can't use that. Come on. All the following are equivalent to P if and only if Q, right? So different scenarios here. This one is for if P then Q, whereas this one is for the biconditional P if and only if Q. So P is necessary and sufficient for Q, right? Is kind of a go-to move. P is equivalent to Q. If P then Q and if Q then P. Wow. If P then Q and conversely, which kind of feels the same to me. Right? And then you're seeing my scammy things. I had to get them to line up, otherwise it would be, I put one on the other side, so I had to just make an empty bullet. Just ignore that. Or you can add something at your own risk. Okay, what if we did something like this? Wait. Let P denote Fred like Cindy. And I totally stole this out of a different textbook, which I think is pretty cute. And let Q denote Cindy likes Fred. Use the connectives and, or, not. If P, then Q. If, sorry, P if and only if Q. All right. Let's try it. Or you try it on your own. I'll pause it one last time. As promised, we'll only do this page. Unless there's something real, can do it. Here we go. Fred and Cindy like each other. That, you could rewrite that as Fred likes Cindy and Cindy likes Fred. P and Q. Well, Fred likes Cindy, but Cindy does not like Fred. Yep. Yeah. That's for F. Fred likes Cindy, but Cindy does not like Fred. The but is going to make an and. And so Fred likes Cindy. So we can start there. That's a P. And Cindy does not like Fred, which is not Q. Right? So the but kind of turns into an and those would be, they would mean the same thing, right? And so, and not Q. If you want to wrap some brackets around this not Q, we'll talk about it next day, but there's order of operations, just like we have BEDMAS, but for logic. And so you don't have to put brackets around there because the negation's always done first. But if you want to toss some brackets on there, you can. Fred and Cindy dislike each other. Wow. That means Fred doesn't like Cindy and Cindy doesn't like Fred. And again, if you want, I'll put these kind of optional brackets around here if you want. Fred likes Cindy or Cindy likes Fred. P or Q. Cindy likes Fred if Fred likes Cindy. So the if starts at if Fred likes Cindy, then Cindy likes Fred. Right? And so you want to rewrite it in this way. So if Fred likes Cindy, then Cindy likes Fred. So it's like this. So the if is always kind of floated to the front. And Fred likes Cindy if and only if Cindy dislikes Fred. Poor Fred. That's P. And this is not Q. And this is the biconditional. I guess I can summarize it better over here. P, if and only if, not Q. Ta-da! Logic. You can glance at the next page. Next week we'll start. I can't believe I don't get to see you until Tuesday. Come on. We'll start building truth tables. to figure out what the truth values are for C. Until then, enjoy your weekend. See you next time on Math 111.